Good morning, everybody. Welcome to Lecture 7. So, we are already in the last week of this course. In this lecture, we're going to be discussing the more practical aspects of CNNs, like how we can load in data, how we can increase the size of our data set and make our models more robust, and then saving, reloading models, tuning hyperparameters in a systematic way, and then finally we'll discuss transfer learning. In the next lecture, we're going to be talking about more advanced techniques and algorithms in the realm of convolutional neural networks, but for this lecture, we're going to focus on the more practical stuff. Okay, so let's begin. All right, so I have shown you earlier in the course how to load data into PyTorch tensors, and we have seen that PyTorch expects the variables in the form of PyTorch tensors, and while we can do this process manually, loading in the data using NumPy or Pandas and then converting things to tensors, and then we can also do the batching manually. We can also use these helper functions provided by PyTorch, which speed up the development process by quite a bit, especially in more complex cases. And especially for CNNs, we usually deal with classification. And when we deal with classification, we have a bunch of images, each belonging to a certain class. And if you don't have particular strategies in place, it would be a little bit hard to code how you're going to assign different class labels to different images coming from different places. So PyTorch basically does all of that for us. It's the only thing we need to do is to get familiar with how the interface of PyTorch works. So one particularly helpful PyTorch helper function is this image folder function. So you can access that from Torch Vision, that datasets, that image folder. And what it does, it's going to look at an image data set, and for example, if we have two classes of images, one is cats, one is dogs, we place them in different folders with different names, cats and dogs, and once we use this helper function to read the data in, depending on which folder each image is located in, it's going to assign a separate label to that image that corresponds with the folder, corresponds with the actual label of that image. So let me show you how it works. For example, we have this data. In this problem, we have two classes. So we put all of the images belonging to the first class in this class_1 folder, and then everything belonging to the second class in the class_2 folder. And as soon as we do this, PyTorch image folder function automatically understands, okay, all of these images belong to this particular class, all of the other images belong to the other class, and it handles that for us automatically. In the case of the Bitmoji dataset, for example, we had these two classes that you're familiar with at this point, and I have put everything belonging to the Arman class. I've put all of my Bitmojis in the Arman folder and all of other people's Bitmojis in the not Arman folder. Okay. So here we go, let's give it a try here. So Torch Vision datasets, that image folder, and what we should give it as an argument is the path to that directory which contains those images. Okay, and once we do that, it creates the dataset for us. And I have mentioned previously that the dataset creation using this syntax actually doesn't occupy the memory with the images themselves. It creates some data structures underneath, but it doesn't occupy the memory with the images. This is why, although we're creating the data set, but you can see that the consumed memory is just 1 megabytes, and the data set is obviously larger than that. This is because this is just a generator object. It doesn't consume all of the memory. It just goes and grabs the pieces of data once we need it, not it doesn't load the entire thing into memory and then start reading from it. Okay, yeah. So once we have created this object, this train dataset object, there are a bunch of useful attributes that we can inspect. For example, the classes that we have, the targets, number of samples. For example, here, if I query the .classes attribute, I can see the class labels, and this is according to the folder names that we had in the data set. And it also shows us how many examples we have in each folder for each label, the total number of samples, and the location. For example, we can also look at the path of a particular image. Okay. So as I mentioned, the train dataset object, it's technically not a generator. We should apply this iter function on top of it to make it a generator, but that's unnecessary details. Okay, so we have created the generator here, and now, just like any other generator in Python, we can start consuming the generator by either looping through that or by using this next function, which just calls the next available item inside of that generator. So when we do that, this is yeah, that's a funny image. Yeah, it happens to be the first image in that folder. Yeah, so yeah, as you can see, once we start iterating through that generator, it's only then that it goes into that folder and loads the data into our Python session. This image is going to come up again. Just okay. Okay, so so one thing that we are usually interested in doing is applying some form of transformations onto our image data. For example, we might be interested in resizing our image, or in some cases adjusting the colors or brightness or some other features of the image. We might want to crop an image or something like that. So PyTorch provides all of that optionality for us. The other thing that we usually do is that right now the images are belong to this particular class, which is a PIL Python image library class. It's basically NumPy arrays. So the first transformation that we're interested in is converting everything to PyTorch tensors. So you have seen the syntax for this, that we can put all of the transformations that we want into one list, and then PyTorch goes through those transformations, and once it starts reading the images in, it also sequentially applies those transformations onto the images. For example, here, suppose that I want to first resize my images and then convert them to a PyTorch tensor. This step is usually always there because we always want to convert things to PyTorch tensors unless you're directly reading PyTorch tensors. And note that for this sequential transformation, we use this transforms.compose function. So basically you supply a list of transformations to this function, and it reads the images, passes that through that pipeline, and then generates the datasets for us according to that. So the transformations are also another parameter that we can feed into this image folder function, as you can see here. Okay, if I do that, so in the first step, you can see that it has resized the images into 64 by 64, and it has also converted everything to PyTorch.tensor. Okay. Now, so this takes care of doing the transformations that we need. Next thing is creating the mini batches for the training procedure. And again, you have seen the syntax for this, but just to review this in more detail, we can use the data loader function for that purpose. So what it does is just takes in the training dataset object that we have just seen, this object that we were able to loop through and read in images. So we just pass that to this data loader, and then it takes care of creating the batches for us. So once we do that, the train loader actually is another kind of generator that if we loop through, we will retrieve batches of images in the right shape and format. And as you have seen, it accepts these arguments. For example, shuffle takes care of shuffling the images. Sometimes we might not want to use the last batch if it's smaller than the typical batch size. That's also an option that's available. And yeah, that's pretty much it. Again, this is just a generator. It doesn't do anything until we start looping through that. So it doesn't materialize until we start looping through that, just like any other generator in Python. Okay. So here I'm applying next onto that generator. And once I do that, it actually goes and retrieves some images. And you can see that here it has created 39 batches, and each one of them contains 64 images, and each image is 64 by 64. So again, this is the shape of the data, 64 images in each batch, 3 channels, 64 by 64. And now we see that we have some memory consumption over here because the data is now in the memory. Okay, questions about train, the image folder, and the data loader? Yes?
What are the other type of transformations that we do on images typically, other than resizing them or changing their type with that sort of thing?
Yeah, just like I mentioned, for images, there is a whole list in PyTorch documentation, the type of edits that you might want to do on an image, changing the ranges of colors, flipping images, rotating them. Yeah, there's a lot of transformations you might be interested in doing. Yeah. Okay. Okay, so in some certain situations, this process of creating the train loader and data loader might be a little bit more complex. I will talk about a certain architecture in the next lecture where we have to feed in, for example, 2 types of images into one network. And in that case, we have to create separate train loaders. And in that case, it gets a little bit complicated, but the idea is still the same. We use the generators to go and retrieve data. That's the idea. Okay. Now, next thing that you might need is that, so right now we have started working on larger and larger models, and you have seen that it takes quite a bit of time to train your models, and usually we are interested in saving our models at some point as either as checkpoints or as the final model for making predictions. We don't want to retrain everything every time that we restart the kernel in our notebook. So in that case, we can store the parameters of the model into a file. PyTorch, again, makes that super easy for us. Torch.save, and then we pass the stateDict attribute, which stores the weights and biases of the model. And once we have that model file on the disk, whenever we want to reload that model, we have to create a model with the same class, same structure, same architecture, and then we simply do model.load state dictionary, and then we feed the model file into that. So the only important thing here is that this function expects the model to have exactly the same architecture, because obviously it corresponds to the same weights and biases. Okay. All right, so here's an example of the Bitmoji CNN model. Okay, let me run that. And then here I have already trained this model and saved the parameters of the model to the disk. So here I'm providing the path to that model file, and then I create the model object. And once I have the model object, I can run this, this method, load underscore state underscore dict, and then I can provide this object torch.load path, and it's going to populate the weights and biases for me with the right values. Okay, one important thing about inference time is that some of the components of our neural network models behave differently when we are training our model compared to when we want to make predictions or for the inference step. What's an example of one such component? So a component that behaves differently when you want to make predictions or when you're training your model. So for example, linear layers or convolutional layers, do they change when we make predictions or when we're training our model? We use the convolutional layers. But the thing is, the weights have already been decided. So we do the convolutions, but we don't do backpropagation. Okay, so that's we don't touch the convolutional layers. We just use them. You learned about a certain kind of layer that behaves differently. Something that's helpful for preventing overfitting. Dropout, yes. So if you remember with dropout, it's randomly turns off a certain fraction of the neurons in a layer. So that's helpful during training, but we don't want to kill our neurons in the prediction time. So that basically adds some noise to the training process, but we don't want to have that once we start to make predictions. So in order to not make wrong predictions with some randomly turned off neurons, we have to make sure that at the prediction time, we should put the model in evaluation mode. And this is the syntax for that. Model.eval makes sure that those dropout layers are out of the business, basically. So you don't care about those. We just run the data through the network in the usual way. So this is very important. And this is the line that you see right before when I do the validation set processing in the trainer functions. Because for the validation sets, we're making predictions and we're evaluating the model. We don't want the dropout layers to affect the model predictions, basically.
Does it mean that dropout layer still works?
No, it doesn't work. So it just gets completely turned off.
So how do we protect our model against overfitting?
No, okay. So the part where overfitting problem is improved has happened in the training procedure. So that's already done. We have included some noise in the process, and we are done with that. At the prediction stage, then we don't care anymore.
So when we're defining model like from scratch, and then we are using it for prediction, we are not using eval because the model has been trained in the current working session.
No, okay. So we have the dropout layers, okay, and we go into training and start training the dropout layers, turn on neurons and stuff like that, and then, okay, we are trained, the model is fixed. Now in the inference stage, we do model.eval, meaning that, okay, just disregard the dropout layers and make your predictions. You don't need to change the model structure. Once you put the model in evaluation mode, it automatically knows it has to turn off the dropout layer. It has to ignore it.
What are the weights of those neurons that drop out, turn them off previously?
Okay, so because this procedure has been randomly applied onto the weights, those weights are still learned through the backpropagation. So for example, you have 10 weights. Weight number 7 has been turned off in first iteration. Weight number 8 has been turned off in the other. But we still learn the weights for those layers in the process. Yeah.
It's not that if it's dropped out, it's not that it's computed in that iteration. You just computed it in a different iteration where it wasn't dropped out, right? Like if 7 was off, it doesn't compute 7. But then 7's turned back on and 8's off, it'll compute 7 in the next one. Like if it's dropped out, it's just computing, right?
If it's dropped out, basically it means that the value of its weight becomes 0.
Right.
Okay, at that particular iteration. Yeah, and then in the next iteration, some other neuron gets turned on. Yeah, yeah, yeah. Okay. Any other questions? Yes. No, there's another type of layer which I'm going to discuss a bit later in the lecture called batch normalization, but we'll get to that. Yes?
Do you ever need to turn it back? Do you ever go like training, validation, training? Do you ever have to turn it back off?
Okay, so if it happens that you train your model, then you do some evaluations, then you're interested in picking up the training process from where you left off, then you have to put it in model.train mode. So yeah. But usually we do the training completely and then we do the evaluation. That's why I don't. But the syntax is somewhat similar. So it's something like this: model.train. Okay. All right. Okay. So an important technique in image recognition especially is data augmentation, and usually it's used for two main purposes. One of these purposes is sometimes we have a training data set that's too small and we want to create more images, but that's not possible, so we make some transformations to the images that we have right now and then feed those to the model in the training procedure. And the idea is that if you want to, for example, detect a cat or a dog or another, I don't know, something else, then, for example, whether the image is rotated a little bit, that shouldn't impact the class, the prediction class, right? So, for example, if the image of I don't know, a smartphone, for example. If it's rotated a little bit, it's still a smartphone. If it's flipped in one direction, it's still a smartphone. So it shouldn't impact the training. And so this is one useful way to augment our data set and increase the number of images that we have in our data set. That's one purpose. And the other purpose that's implicit in what I just mentioned is that we can make our model more robust to variations in the data set that we have. For example, if we have always trained our models on images of, for example, of some object that always happens to be in an upright position like that, then when it sees an image of this same object that is in this position, it's not going to detect that successfully. So we want to guard against such variations in the data set, and that's usually the more important purpose for data augmentation. Okay, so let me show you an example here. So this is a Bitmoji of mine, and then I'm gonna create the image PyTorch tensor, and then I'm gonna make a prediction on that using the model. Here I'm passing the image tensor to the model and then passing that through sigmoid because it's a binary classification problem, and then applying the condition and finally making a prediction. So it predicts it correctly. Okay, however, if I flip my image like that and now pass that to my model, you can see that it no longer detects the image correctly. It no longer classifies it correctly. So this image is still my Bitmoji, but it's unable to detect that because it hasn't seen an example like this in the data sets. Okay. So this was just one example, but if it makes more sense to see how the model performs if I flip the entire, flip all of the images in my data sets. So I've created a function here called evaluate, and it basically just puts the model in evaluation mode and computes accuracy on the validation set. Okay, just a helper function. This is not too important. And now, here, see what I'm doing here. So here, I have my transforms.compose function, and I have a random vertical flip function applied in the first stage of transformation. And then that P is the probability of flipping images, and I've set P equal to 1 so that I flip all of the images in my data set. Okay? And the usual stuff after that, and I'm using a batch size of equal to the size of the validation set so that my accuracy is computed for the entire validation set. That's a very important detail. Okay, you can see that the accuracy of the model basically dropped to 50%, meaning that we're not doing anything useful. And let me turn this off. Random vertical flip. Now it's 98%. Okay. Now, question for you. What do you expect to happen if I do something like this? Horizontal. Would it drop to 50% again or something close to that? Would it remain close to 98%? Yes. Oh, okay.
I would guess that it'll maybe be not, it'll maybe be in between two.
Mm-hmm.
It looks for like certain structures, like all your bit modes have the same kind of hair structure, for example. It would be here now, so it's not at the top of the image.
Mm-hmm. Mm-hmm.
Some of it kind of is, so it might pick up a
Right.
tiny bit of that, might get like
Mm-hmm.
the eye towards the top, or it kind of, but like only half of the stuff, so not good, but a little.
Yeah, yeah. I mean, the faces are symmetric about, for example, the center line. So we sometimes get images that, I mean, basically we get flipped images in the data sets itself. So we can expect that because of the symmetry of the faces about the vertical axis, we expect this not to affect the accuracy too much. So let's see. Well, 92%. Okay, so the vertical flip entirely destroyed the model, but horizontal flip, that's something that the model tolerates quite well because the data set is representative of cases where we have flipped images as well.
A horizontal flip is like a mirror flip?
Yes, a mirror flip, yeah. That's a vertical flip and that's a horizontal flip.
Oh, I interpret it as a rotation.
Ah, okay. Yeah.
Argument is still right.
Okay.
Well, I have a question as well.
So your argument was based on a,
90 iteration, which I thought would be.
but it turned out okay.
I didn't think it would be 92. I thought it would be like marginally better than vertical.
Mhm,
Because
yeah.
again, like the eye might be here.
Yeah, makes sense, yeah.
But horizontal makes sense if you do that.
Yeah. Yeah.
So I see that here you're flipping every image, right?
Yes.
Is it the case where you want to include both the flipped image and the non-flipped image in the same data set, or do you not do that?
Yes, that's typically the case. So we include both of the instances to tell the model, hey, it's normal if you see this image and also its flipped version.
Right. And you would put that in the data transform to have keep same image and add flipped
Yeah, so the thing is, if you want to have the same size of data set, you just set this parameter, this P, to, for example, 0.5, and in that case, it only flips half of the images.
But what if you want double size?
It wouldn't double the size. Yeah, if you want to do that, you have to create basically two tensors and then concatenate them in order to create a data set that's double the size. Yeah. Okay. All right. All right, and that's not the only variation that we want to guard against. For example, if the image of a dog is slightly zoomed in, we also want to make the model robust to such a change and stuff like that. For example, in that situation, we can use cropping and then resizing the image back to the size that we like. Yeah, we can do all those kinds of things and then train the model. Okay, so let's see an example. The outputs of these transformations. For example, here I do vertical flip with a probability of 50% and random rotation with up to 20 degrees. So these are the Bitmojis. And one downside of this is that we get these black margins around the images when we rotate them. And this is In this case, we can fix this by applying a white color to the margins, but in other cases, this might be problematic because the model becomes biased toward images that have such a margin around them. Okay, so this is why in the examples that I have in the lecture notes here, I only apply flipping, which doesn't cause this problem. Okay, so I have a model here that I have already trained with the augmented data set. So with having random vertical flips and random horizontal flips. And then let's load that model. And now this is the image that we used for testing. And now if I use this augmented model, I can do this and it predicts the correct class. And now I can evaluate the model on the entire validation set and see how it goes this time. So yeah, it's pretty good. Now the model is robust against such variations. Yes?
Why do we flip and rotate our training images rather than maybe rotating our filters and stuff?
We don't rotate the filters, do we?
I mean, we don't, but we could.
How about rotating the filters instead of that?
Yeah.
Yeah, so you can implement ideas that achieve such a thing. I mean, invariance techniques come in many different shapes and forms. It's not directly about rotating the filters, but something that's done in other layers of the neural network. It is possible, it is done in some certain situations, but we won't discuss that here. It's a little bit too complex. Yeah.
Is this saving the rotated images into new tensors? And if so, would you that would create a lot more storage space?
No, it actually, so because again, it's a generator, it does that on the go. So when it loads the images, it does the transformations at that time, yeah.
Are there kernel-based methods to effectively impute the pixels that are lost by the rotations? Like it was black there, you said you could fill it with white. What if you don't know that it's white? Is there a method where you can take the average of adjacent pixels to the edge and impute?
Yes, certainly. You can do those transformations. I don't remember the exact name of the function that achieves this, but there's certainly such functions that do achieve this. You can do extrapolations, interpolations, stuff like that. Yeah, for sure, yeah. Okay, this idea of rotation invariance. So our neural networks are translation invariant, but they're not rotation invariant. Especially in point cloud data where you have 3D objects, this idea becomes very important, and you want to make your models rotation invariant as well, and that leads to a certain kind of architecture called point net. You might want to look into that. And in that case, there is a special matrix transformation done on the inputs of each layer that basically achieves this rotation invariance. Okay. All right, any remaining questions about data augmentation? Yes?
So these are two-dimensional images of two-dimensional things. Is there a way to make it invariant to rotations that on an axis that isn't facing the camera? Like if you have a picture of a face, is there a way to make your image resilient to the face rotating around an axis that doesn't face?
Yeah, that's a good question. Is there a way to make our model robust against basically change of angles, not along the axis that's normal to the plane, but along other axes? So there is a concept called isotropy matrix in image processing, which actually takes care of this same thing that you discussed. And this is particularly useful for some applications. For example, when you have a bunch of images of kind of the same scene, and then you want to stitch them together, it's important that you look at all of those from more or less the same angles. So in that concept, there's actually a neural network architecture that does image stitching and uses image isotropy in order to achieve this. So in that case, we don't augment the data, but we incorporate that particular transformation or invariance in the structure of the network.
Okay, it's an architecture thing.
Yeah, yes. Although you can actually, there are computer vision packages like OpenCV that do this kind of transformation on images if you want. You can train your neural network with just augmented data, but it's usually much less robust than if you actually incorporate those assumptions into the structure of the model. Okay, so let's see, we have a bit more time. So I've marked this section optional. It is optional in the sense that I'm not going to ask questions about this on the quiz, but it's a very important thing to know and to apply. So we have learned previously that normalizing inputs to a model, for example, in lecture 2, I guess, I showed you an example of doing gradient descent on data that for which the scale of the dimensions are different. And we saw that there is an optimization problem when we have that, and we usually scale our data such that we have the same scales in all input features. So if such a thing is helpful and good, why not apply the same thing in between the layers of a neural network as well? Because previously, what we worked with was a simple linear model. There wasn't many layers, there was just one layer of transformation. So you can think of a neural network as a feature generator per each layer. So each layer can represent new features for you. The output of one layer is the input to the other layer. Okay, so at each layer, it makes sense to also normalize the inputs to the other layer as well. Okay, so in that sense, we have this technique called batch normalization, and what it does, it normalizes the data based on the batch that the training process is currently working on. So, it's usually applied before the activation function of a layer for a neural network. And this is the way that it's applied. So the data is centered around 0. Usually unit variance is used. However, the thing is, because the batch that we are currently taking in, if we compute its mean and its variance, it's not going to be the actual mean and variance of the data set. We also introduce these two parameters, gamma and beta, and we allow the model to learn those parameters. So we say, okay, this might not be the actual mean and the actual variance of the entire data set, so we allow the model to decide what are the optimal values for gamma and beta. And okay, the end result is that it rescales the data, normalizes the data. Okay. So the batch normalization helps to stabilize the optimization process. As we have seen previously, if you're not careful about the learning rates and stuff like that, we might run into numerical instability problems. So batch norm helps significantly with that. The other important feature of batch norm is that it adds some sort of regularization to our model. So in deep neural networks, it has been empirically shown that introducing noise into the data usually helps with generalization capabilities of the model. We have seen an example of this with stochastic gradient descent, right? It introduces some noise, and we might initially think that this noise is detrimental, but it's not, because it helps the model to avoid fitting too well to the data that we have. And this works more or less in the same way, because the mean and the variance that it estimates is based on a certain batch. It introduces yet another level of noise into the model, and it has been shown that it works pretty well. It helps with preventing overfitting, it helps with numerical stability, it helps with the problem of vanishing exploding gradients as well. The funny thing is that the people who actually proposed this method, they justified and argued that this is because the batch norm works well, because it redistributes the data in the same way among different layers. So it helps with the problem called the covariate shift problem. And then it turned out that it's actually not doing much. that problem sometimes doesn't even exist, and it's due to other reasons, for example, like the regularization properties of this batch norm, that it's actually helping the models to train better and generalize better. And again, a recurring theme in deep learning, I've brought this quote from this paper in 2018, which says, somewhat shockingly, despite its prominence, the prominence of batch norm, we still have a poor understanding of what the effectiveness of batch norm is stemming from. So even though batch norm has been around for 7, 8 years now, it's still not completely known why it helps so much. Questions? Yeah.
So when we talk about the cases that you're using normalization with numerical features, for example, one feature having like a different scale than the others. So what are the cases of like, let's say, using this type of normalizations on images? Is it like having a white background or something? What causes that like unbalanced values that we need to use normalization?
Oh, okay. So with images, we usually don't have that problem because the pixel values are limited between certain numbers. Batch normalization in that manner does not affect different dimensions. In this context of batch norm, it affects the outputs of each layer that might be different across different filters, different features, or between the layers. It's not exactly in that sense. You're right, because usually image data is usually limited between numbers. It's usually, we don't have that problem of that difference in scales that much. Yeah.
So I have a question just about how this interacts with the activation functions.
Mm-hmm.
Kind of two questions. The first question, so you said it's before,
Yep.
right? So if this is a normalization that's centered around 0, doesn't that mean that in theory half of our data points then go below 0, and if our activation function is ReLU, doesn't that 0 half of our values?
Sure.
Or is that taken care of by the beta?
Yeah, that's the thing. So the first intuition is that, okay, normalization helps because of this and that, but when we do that without allowing for these free parameters, it turns out not to be that helpful. So this is why we let the neural network decide what are the optimal values in this layer for this particular batch norm layer for the normalization. It doesn't always scale to like unit variance and 0 mean. It's just the first transformation, and then it decides on the eventual transformation.
That kind of answered my second question too.
Okay.
My second question was like, doesn't sigmoid do something similar by mapping values from 0 to 1? But I guess that's not the right place to put it. This will learn a different value to shift it this better place.
Yeah, so the sigmoid does that in the output, but we apply this before that, so it helps with the saturating regions. If you use ReLU, then in that case, you are also able to apply batch norm after the activation, and it has an effect, on that. Yeah. But usually it's applied before the activation. Yeah. Again, there's no rule to tell you that you have to do this. No, people have achieved success with both ways of implementing this. Yeah. All right, it's a good time to take a break. Let's be back in 3 minutes. All right. We are back. Okay, so let's discuss hyperparameter tuning for a little bit. Okay, so so far in the lecture, whenever you have asked me how you can decide about different hyperparameters in the model, like the learning rate, the number of nodes, number of layers, stuff like that, initializations, I've always told you that you have to do experiments with your model. So that's still true, but there are more systematic ways to do experimentation rather than just putting in values for learning rate and for different things that we have in the model, and then try the results. So we have discussed this already in other courses that when we are searching for an optimum value, grid search is usually the worst that you can do unless you have one-dimensional data or something that's super quick to compute. However, if we can make use of the directions of the changes, and if we can be more smart about the way that we search for optimal values, then we can basically make the process much more efficient. So the gradient descent is one example of that. Instead of computing all of the possibilities and then finding the minimum, we use the direction of gradients in order to guide us to the minimum or maximum value. So same is true here for tuning hyperparameters. There are a couple of packages that can help you with that for tuning hyperparameters in neural networks. A particular example is called AXE, which is created by Facebook, and it uses Bayesian optimization to tune the hyperparameters. So basically creates distributions in different dimensions and applies updates to those distributions once new data comes in about the training procedure. Basically what it does, let me run these codes here. Okay, what it does, it starts training the model with certain parameters and then obtains some accuracy values, and then it uses those accuracy values to update the previous distributions of the accuracy over those parameters. And then new data comes in, it updates and updates and updates those distributions, and then finally it uses those to compute the best values. What you have to do for it to work in terms of syntax, you have to create a train function that takes care of the training and then returns a trained model. That's what it does. And then we also need an evaluate function that measures the accuracy, whatever measure you have. And we have defined this earlier in the lecture. So that is what we're trying to optimize. For example, in this case, I'm trying to optimize the accuracy of my neural network. There are other measures that you can use. For example, you might be interested in the, suppose that in the true positive rate or something like that. You can also have a different evaluation function for that. In this case, it's just accuracy for me. And then once you do that, you create another function called train evaluate, which does the training and then does the evaluation and returns the value of the accuracy to you. And finally, I mean, the syntax is not important here. It's the idea that matters. So here it has an optimization function, which I have imported at the top. And what's important here is that it takes in ranges for the parameters that you want to optimize. For example, here I want to optimize the learning rate, in this case, LR, and then beta 1, which is another parameter for the optimizer. And these ranges are things that I decide, okay, I want to search in this region and in this region. And then once I provide those values, and then I specify how many trials I want to run in order to create those distributions for my parameters. And then finally, it will output something like this, runs multiple trials, and then it gives you the best parameters for you that will give you like the best accuracy values. For example, here with these two values, learning rate of this particular value, beta 1 of this value, you get this accuracy of 86.91. And one other thing that's very intuitive, it shows you these, creates these plots for you. For example, here we have the learning rate, we have beta 1, and you can see this region for the distribution of accuracy, and you can see that here you're getting the largest or the maximum accuracy for the model. Okay.
What creates those discrepancies?
Which discrepancies?
So there's the obvious, like, correct region,
Mm-hmm.
and then there's random blips that also look like, okay, why are those there?
Sure. I mean,
Like, they do something.
it's largely a linear model, and it has a very complex behavior. So we can't really say. So just like we've talked about this for finding like the minimum value of the loss function, there might be several global minimum values that you might converge on. There's no simple explanation to say this is why we have this many minimum values. It's the same thing basically here. Yeah. So some of these values, if you use those particular combinations, you'll also get the best accuracy. But it seems that they're kind of condensed around this region. It's a safer region. And then it also plots the accuracy output while those parameters are changing. Okay, so again, the most important takeaway here is that instead of grid search, we use these approaches, which are more smarter ways to do optimization, because computations with neural networks are very, very expensive. Okay. So, explaining CNNs. Again, this part is optional, but I think it's something nice to know. So, sometimes for example, in the case of Bitmoji dataset, we have trained the CNN, we are getting a very good accuracy, but we might not exactly know what is it that the model uses the most in order to make those predictions. For example, there are a lot of funny, interesting cases on the internet that shows weird predictions by neural networks that have been very well trained. For example, situations where the model correctly classifies a wolf, for example, in an image, and then they found out that what the model actually has been looking at is the scene behind the wolf, which is usually an area covered with snow, and it's just predominantly a white color. So it's not actually the animal, it's the surroundings about the animal, around the animal, that makes the model, helps the model to predict. So we train the model, it works very well, but sometimes it uses surprising features in the image to come to those conclusions. And that is not something that we always want. Yes?
So, coming from a functional kind of perspective, sometimes you could, for instance, instead of having pictures with wolves in the background, you could save the image as a PNG file and like only cut out the wolf. Can you train neural networks on images that aren't square like that, that have this really weird shape that are of a wolf only?
Yeah, I mean, I would say yes. If you can do that transformation and all of the future inputs to the model are also images that don't have a background and only focus on the object, for sure, then the only way that the model can find something out about the image is the actual object that it sees. But usually that's not the case.
Okay.
Yeah.
It's a bit more difficult because every image has a different size and a different.
Right. Yeah. Okay, so let's see how what is the understanding of our Bitmoji model about our data set, how it makes its predictions. So there are, again, a couple of packages I've mentioned here. I used this Captain package, which provides a number of algorithms to explain the model. You can read the documentation if you're interested, but I'm going to discuss one of the more simpler ones to understand, which is the occlusion model. Let's see how it works. Okay, so I have my Bitmoji CNN model. I put it in evaluation mode. Everything's good. here we go again. Okay, I'm not gonna. Okay. Okay, let's. I don't know. This one, no. I don't like any of these. Okay, this one, for example. Okay, so let's see the output of the occlusion model. I'm gonna tell you what these all mean in a moment. Okay, I've asked the model to predict the output, and this is the output of the occlusion function. So what this method does is that it takes in that particular image, and it starts covering certain areas of the image with any color that you want. For example, here I've set that color to be white, and that's specified by this parameter over here, baselines, and 1 means just white, because the background is a white. And it places those squares of constant values over the image, and then looks at the output. And it starts noticing where is it that the model changes its decision on the classification. What are the areas that if we put that pixel cover on those areas, then the model, in most cases, it changes its decision about the label of that class. So for example, you can see that here, when this function has placed those square patches on the image in these areas, it has majorly affected the prediction made by the model. So it means that the model is basically kind of looking at the hairstyle, forehead, or a little bit around the eyes in order to make those predictions. So this could mean that this is the area that's most different compared to other images that I have in the other class. For example, the other Bitmojis have a different hairstyle, different composition of facial features and stuff like that. And it makes sense in this case. And we can also run maybe a couple other more instances here. Okay, the prediction is correct. Again, it's kind of it seems that it's focusing on that area. So you can see that this method is very understandable, very intuitive. It just covers areas of the image and then looks at the prediction, looks for when the model changes its decision about the classified label. Okay, questions about this? Yes?
The selection of the baseline, is that because you said the training data has white background?
Yeah. That's something I've decided because of the background. You can use other colors. Like if you don't specify that parameter, it places a gray patch on the image. Yeah, that can affect the way that the model is trying to explain things in terms of occlusion. But in this case, it's okay. Yeah. And the parameters that you can see here, we have the sliding window shape, the size of that patch that's being placed on the image, and also the strides or the steps by which it moves those patches over the image. And then the rest of it is just making predictions with the model and then using the syntax provided by that function. So the important part is here, basically, the strides, the window shapes, and the baseline. So this is a relatively simple method. There are other more sophisticated methods, for example, the gradient of Shapley values. I guess this stands for Shapley additive explanation or something. So what it does is basically takes the gradient of the prediction by the model with respect to the inputs, and using that, it finds which direction it has to take or which features are most influential on the gradients of the predictions with respect to the inputs, and uses that information in order to tell you what are the most important pixels in the image. So the background of this method is a little bit technical, but again, takeaway is that it helps you to tell what the model is using in order to make those predictions. In this case, again, you can see using this other method, we can still see that the model is basing its predictions on that area of the image. Okay, questions? Yes?
General question on the slide and the slide window that you said. Why would you want to change that? Like, is there, like, apart from computational benefits, like if we change the slide, maybe the size of the result changes, so maybe there is a computational benefit. But is it like stride one is going to do the maximum computation, so why not just go with just that all the time?
With stride 1? So yeah, the biggest issue with varying the number of strides and the window size and the issue with choosing smaller values for those is the computational effort. If you start experimenting with that, even with like 256 by 256 images, you'll see that it takes a few minutes to do this computation. So it's not worth doing in most situations. The other thing is that it also depends on what are the features in the image and what are the length scales of those features in the image that you're looking for. If they're on the length scales of, for example, 50 pixels, you don't really want to choose a window size of 2 pixels because that won't give you much information, basically. You want to use the same length scales. Other questions? Yes?
If you want to see why a model classifies a picture as not Armon, would they also look for that hairstyle kind of like?
Oh, we can try that actually. I have to run through the generator to make that work. So, for example, for I have to consume the generator up to the point that it reaches the other class. So I can do gen and then say if q equals, I think we have 1,000 or 1,300 something. Then let's then do this. And then break the loop. Okay. Do that. All right. Okay. All right, let's see. Yeah, okay. So in this particular image, it looks like it looks at other features in the image. For example, one explanation could be that my Bitmojis don't include a case where you have that 3D text behind my Bitmoji, and that's why it's focusing on these areas. For example, that could be one explanation. Let's try a few more. Okay, this has a white background, maybe helpful. Okay, so it looks at the shirt for this case. It makes sense basically. Yeah. Okay. All right, so let's talk about transfer learning for a bit. So far, I have been telling you a lot about the fact that neural networks can be viewed as giant feature engineers, and here we're going to use that feature of neural networks in practice. So one important thing to note is that if you have trained a CNN on a large data set that has a variety of data, a variety of classes, variety of different objects, then you kind of can claim or assume that your model has learned useful features, general useful features that can be used to detect any kind of image, more or less, because there are some lower level features that are dominant in any image, the lines, the edges, the different shapes like circles and stuff like that. And then we have more higher level features based on those ones. And those, again, could also be helpful in classifying other images. So for example, if you have a data set that's been trained on, let's say, I don't know, on the images of of animals, of cars, of airplanes, and stuff like that. Those features that the model has learned could also be helpful in, for example, classifying different types of buildings, for example. Because again, the features are kind of the same. You want to detect lines, you want to detect compositions of those lines and edges and all that information. So this idea is what transfer learning is about. We have a pre-trained model that is complex, large enough, and it has been trained on very large data sets. And we kind of, because we have that model already pre-trained, we can take the model and use it as a feature engineer. And then, because it basically takes care of compressing the entire information inside of the image down to like a couple of important features, we can then use those features and pass them to any classifier that we like. That's the core idea behind transfer learning. And it's a very, very powerful idea, actually. Okay. For example, here are a couple of famous CNN architectures: VGG, ResNet, Inception, MobileNet, and there are a lot of others that you can look into. I also have a link that I will update the lecture with, which you can look at all of the different image classification models, their accuracy on the images that they've been trained on. I can actually show you that. For example, okay, here we go. So I can give you the link for this one. You can see that here we have different models for image recognition with the year in the x-axis and the total accuracy of the model on a certain type of data set. And you can see that the accuracy have been rising over the years. And here you can also see the model along with the accuracy of it on this data set, the number of parameters, and also the original paper that suggested this model. So this is a very long list, but it's a very comprehensive resource for you to look into if you're interested in seeing the performance of different image classification models. Okay. Let's go back to this. So these are a couple of such architectures that I mentioned here. There is a couple of famous data sets for training image recognition tasks. One of them is ImageNet, which is, today it contains around 14 million labeled images with 24,000 categories. In 2012, when AlexNet was proposed, it contained around 1.2 million images with 1,000 classes. So 1,000 different kinds of objects exist in that data set. It's a very, very popular data set for training and researching image recognition neural networks. Okay, so there are not only two, but two more important ways to do transfer learning. One is to use it as a feature extractor, okay, just like I discussed, and then you can detach the end. There you go. Okay, so the two ways are, one is feature extracting, so detaching the head of the neural network and then attaching our own classifier layers to that. The other way is that we use it as a feature extractor, but we can also selectively unfreeze some of the layers and do fine-tuning of the weights for the job that we have at hand. Last year, we actually had a capstone project that benefited a lot from transfer learning. So there was a company designing a specific device, and they were interested in detecting a very special class of objects. So instead of doing the whole training ourselves, we just used a pre-trained model and then used it as feature extractor, and then we did transfer learning, and then finally we did some other stuff like pruning the network and stuff like that, but the idea was essentially the same. Okay, so the point is there's no need to go and train your own model from the beginning. You can use the pre-trained models and then do some fine-tuning and tweaks in order to adapt it to your own data. Okay, so there are a bunch of these famous architectures already defined in PyTorch that we can access. For example, there's a famous architecture called DenseNet, and you can load that model using this syntax. And when the thing that I have here, weights equals this, it means that I want the weights of that pre-trained model to be loaded into my model. And what DenseNet is, it's basically a convolutional neural network with multiple stages. It's the important thing it does is that it creates those highways of information. So instead of passing everything sequentially through the network, it also adds some skip connections to the other layers that we have in the network. And that helps with feature reusing and gradient propagation and a lot of other nice features that we have. And this is a very capable architecture. Okay, so the details of the architecture are not that important. You can go look at the paper and the resources that I have mentioned here. But the idea is that there is this huge model already pre-trained. We can just load it and then use it for our purposes. You can look at, let me load this. The first time that you run it, it's going to download those weights and biases. And then if you look at the last layer, you can see that it's a classifier layer. That's the last layer in the model. As you can see here, we have a classifier that's going to detect the class of that object. And you can see here that it says classifier linear input features 1024, output features 1000, because we have 1000 classes. Okay, so let's take a look at the first 10 ImageNet classes. You can see a bunch of different types of objects. Okay, this is just to show you that we have a lot of different classes, a variety of different objects. Let's use the classifier just as is. So we have the image of this cat, and if we pass that to DenseNet, here we go. These are the top 5 predictions of the different types of cats that it can be. Or if we have an image of a cheetah, like we had in a lab, we can also pass that to DenseNet. It says, okay, the first prediction is cheetah, then leopard, then lynx, and so on. Okay, so this is using the model as is, and then we can use it as a feature extractor, just like I mentioned. The way that we can do this is that, first of all, we freeze all of the parameters in the model so that there is no gradient computation updating of the weights. Okay? And then we're going to replace this classifier with our own classifier layer. So here I'm introducing a new layer here. Okay? This is a different classifier layer. And then I'm going to set the last layer of DenseNet to my own layer. Okay? And then once I do that, you can see that it's been replaced with a different layer. Okay? And then now this is a network that I can go ahead and train. If I do that and train it just as any other network that we have so far, the trainer code is not too important. Okay? We get accuracies like this on the data set that I have. So this is training the DenseNet, not the DenseNet actually itself, but only the classifier layer that's attached to the top of DenseNet. Okay, and you can see that we get these accuracies that are pretty good. So this is trained on the Bitmoji data set, if I'm correct. Let me see. Okay, yeah. So train directory and valid directory pertains to the Bitmoji data set, and you can see we have easily acquired an accuracy of 85%. Okay, so this is by training our own classifier. The other thing is that we can cut the network at that point where the classifier exists, and then pass the data through the network up to that point, okay, and then extract those features that are generated by the model, and then pass it to any classifier that we like. So here, I'm defining a function that basically extracts those features from the one to the last layer, and then once I do that, I replace the classifier with identity matrix, meaning that we don't do nothing. We pass the data through the network up to that point, and then the rest of it is just identity, ones. Okay, and then once we do that, we can pass our data to any classifier that we like a logistic regression model. Okay, and at that point, let's see how it performs. I don't do the training here, but if we do that, we'll get something around 180%, 100% and 80% for the accuracies. It takes a little bit to run. Okay, let me also run this. Okay. So it takes a while because it's passing the entire data through the network, which is a giant network, and extracts those features at the end of the network right before the classifier. And then once we extract that, yeah, we can pass it through, we can pass it to a logistic regression, and you can see that we have achieved a training accuracy 100%, validation accuracy of 81, which is pretty good. We have just basically used logistic regression. The other approach is that we can load the same densenet model and then attach our own classifier layer. However, we don't freeze all of the weights and biases of the network. We basically allow them to fine-tune themselves to the data set that we have. Okay? So the only difference here is that we don't freeze the entire network. We use the existing